Next, we're going to have Dr. Haohuang Wen. He PhD from Ohio State last year and stayed at ICDT for postdoc for a year, and now he's joining a startup called SE-RAN.
Okay, thank you very much for the introduction and good morning, everyone. So today I'm excited to talk about the security research on 5G at ICDT. So this is slightly different from Doug's perspective. In the industry, we are more focused on like as an academia researcher. So how could we approach 5G security and building understanding like the unaddressed vulnerabilities in the 5G space, as well as developing countermeasures. How do we address those problems from academia perspective? So first of all, I would like to thank my 5G team from both Ohio State and the SI for their contribution to all these research works. So, like cellular networks are one of the most prevalent way for you to connect your mobile handsets to the external internet. So, so the cellular network has been growing tremendously over the past few decades. And right now, I think the most widely deployed standard is the fifth generation standard, which is the 5G network. And 5G, the most visible upgrade is the speed. So we can enjoy like high speed access to the internet up to a few gigabytes in theory. And 5G also brings a lot of different applications, not just for some mobile internet connection, but also enabling like massive IoT connections and applications in many other domains like medicals and robotics and factories. Those are starting to also deploying 5G networks in those spaces. And 5G also brings like new control functions for operators to manage their network functions, like network slicing is one example. Then they can divide those network performance into slices and allow different groups of devices to connect. So before diving into the 5G security landscape, let's first review a few terminology in 5G, which will be used throughout this talk. So in the 5G, typically, we have the end user devices, often referred to as the user equipments. So that's not just involve the handsets or the mobile phones we are using, but also like the tablets or even many IoT devices like cars or drones. They are all those devices with cellular capabilities. They operate like through like a SIM card or an eSIM card, and they can also access internet. We are generally referred to as the UEs. And then near the edge, there's the radio access network. So we commonly know those things as base stations, base station towers, or we call it the RAN or the radio access network. So those are responsible for relaying the user traffic at the edge back to connect those to the internet. And then there's also like the 5G core network functions as the backend or the backcore network that usually is owned by like an operator or carrier that has deployed virtualized network functions, logical components at the cloud that are responsible for some network session management or security functions and so forth. So that would connect the users basically to the backbone internet access. So within the security space, actually over the years, the security community has discovered numerous attack surfaces and numerous attacks. And this is just a screenshot coming from a 3GPP specification 33A09 that just show like a part of those security attack terminology, include like active attacks and how describing how the attackers can launch jamming attacks, overshadowing to override the signals, how they can launch message attacks to exploit the 5G protocols, as well as the private attacks and how the attackers may perform sniffing to exploit and obtain those user information. So just a tip of the iceberg. So more recent example coming from 2024 is a group of researchers from the University of Florida. They discovered over 100 security flaws in the open source LTE and 5G network implementations. And they actually covered most of the major open source 5G core. Like as you can see in this table, actually many of those open source 5G software like Open 5GS and OAI, Magma Core, those are quite prevalent in the academia and also some of the industry perspective. And those 100 vulnerabilities can be exploited actually by using some authenticating cell phones or malicious radios so that they can, if the attackers know those vulnerabilities, they can use those devices to send malicious signals, basically to exploit like the base station and the 5G core network functions by to disrupt basically the services and compromise the security and privacy of the users. So what do these unaddressed security vulnerabilities in 5G imply? Well, we show that actually this is quite feasible to for attackers to exploit them in practice. And the community has also found a couple of common threat models how an adversary would exploit a 5G network based on the unaddressed vulnerabilities within the protocols and the implementations. So for example, nowadays there are many software-defined radio devices. So basically, attackers can operate on those SDRs, constructing like malicious devices like UEs to send out those signals. So basically, perform jamming attacks, flooding the base station with protocol signals to perform denial of service attacks. And rogue base station is another common issue, like IMSI catchers, like stingrays. Those attacks are actually implemented with using the rogue base stations that can use high signal strength to attract nearby user devices to connect and then extract those user sensitive information. And more recently, there are also man-in-the-middle attackers sitting between a legitimate user and also the base station so that they can hijack the communication channel between the UE and the base station or perform eavesdropping attacks. So these are all the attack surfaces covering like the wireless attack surface between those devices and the base stations. And like on the cloud perspective, there are also attacks that can happen, like malicious base station software. So many of the base station software, they are actually virtualized and deployed on the cloud, and where those supply chain threats and malware could happen, as well as the core network functions. There could be malicious network function nodes like malicious AMF. How those compromised network functions can also easily exfiltrate the 5G network and compromise the user security. And we also show that it's actually quite practical for attackers to launch those attacks in practice. So nowadays, the 5G space is actually quite open, and there are a lot of software-defined radio devices that are available on the market. So you can spend a couple of $1,000 to buy a software-defined radio devices, and you can easily program those devices with like your laptop or even as small as a Raspberry Pi. And those can be, and there are already many open source 5G software stacks are available, such as Open Air Interface or SRSRAN, and those are the leading examples in the open source space. So by doing this, attackers can inject like malicious logic, programming those devices with malicious signals and attack logic, so that they can instantiate like a portable malicious user equipment, like a man-in-the-middle base stations or like a IMSI catcher, basically, to carry out them in practice and attack those real-world 5G networks. So in summary, what are the reasons why there's so many unaddressed vulnerabilities in 5G? Well, I think we summarize a couple of reasons. And the first is the cellular protocol standards are actually highly complicated. So those are actually defined by the 3GPP standard body that involve like millions of pages of specifications, requirements, and all those are mostly in natural language, defining how you should implement security and what are security requirements and how you should implement like a GNOB and a secure 5G core network function. And that becomes really difficult for the vendors to implement those functions in practice. And as I said, the 5G is a highly complex ecosystem, involves a lot of different components from edge to cloud. And those are actually exposing a lot of different attack surfaces via various channels, including the wireless IF channels, the supply chain, and the cloud. And then there are also fundamental design limitations within the 5G protocols. So the picture on the right is just showing like before a UE gets an IP address from the network. So what are those procedures needs to be going on between the UE and the network to establish the authentications, like the security procedures? So those are a lot of 5G specific protocols going on. And those are actually not protected by any encryption or integrity protection. That means those signals can be easily exploited by an attacker to perform the attacks that I just now mentioned. And from the implementation perspective, the 5G software can be highly vulnerable because of the numerous implementation errors and bugs that the RAN or the UE the vendors they implement faulty code within their software. And finally, there are also many practical design constraints, like the carriers often consider like performance of the network, like considering the overhead as well as the user experience. And those are often put first before security. And they may not like really need to implement some security functions before those security threats actually happen. So those are one of the major reasons that we summarize of why there's so many vulnerabilities in 5G. So at ICDT, we actually conducted 2 lines of research. One on the offensive side, how we can try to find more vulnerabilities, demonstrate their security impact so that we can report that to the corresponding stakeholders and vendors so that they can fix those vulnerabilities and also advocate for better protocol designs and defenses. So from the offensive line of research, we focus on a lot of different perspectives. Like from the UE perspective, we design some reverse engineering framework that tries to analyze the baseband and the smartphone firmware to try to find out vulnerabilities that can exploit the baseband using the baseband commands we can extract it to like how to show up those vulnerabilities within the Android smartphone baseband implementations. And then MobiDojo is another recent work we have developed. Mostly is for a virtual security combat testing platform for security researchers to use those platforms to reproduce any security attacks in an isolated virtualized environment. And we also try to find vulnerabilities in many open source 5G implementations like OAI or SRS-RAN. So we focus on the angle of discovering logical bugs, such as the non-compliance to the 5G CGPP standards, using automatic framework employing large language model-based agents to do those vulnerability scanning. Yeah, and so by doing this, as I said, we want to raise the community security awareness, report those vulnerabilities to vendors so that we can, by demonstrating those exploitations, so we can have, hope we can have more better protocols and defenses against those threats. And on the defensive perspective, we also developed a few research works that try to solve those issues. One of the first work is that we developed some visibility tools. Basically, if you want to detect attacks, and the first research problem to solve is that you really need the corresponding security telemetry, the right data for you to detect those attacks. And that's actually not solved in the current security community so far. And we developed like the first security telemetry called MobiFlow that models like the UEs and the RANs state transitions and also protocol level behaviors so that we can facilitate a number of different applications like intrusion and anomaly detection applications. And by then, we also developed defenses at the smartphone perspective. We developed IL Defender to prevent and block malicious SMS attacks from the radio interface layer. And then 5G Spectre is another work we have developed using the security telemetry to perform rule-based IDS on top of the Open RAN platform. And then recently, we also explored the possibility of using AI and large language models to detect unseen anomalies and threats and explain them at the edge. So all those defenses we have developed are integrated into the emerging architecture called Open RAN, and I will go into that in a second half of the presentation. So I will briefly go through 2 major works here, including MobiDojo and the AI works we have developed on Open RAN. So the first work I'm going to talk about is MobiDojo, which is the first virtual security testbed we developed, and we have open sourced it to any security researchers in the domain to use it. So the key motivation of this MobiDojo testbed is that, so nowadays, actually, as I said, there are many open source 5G implementations like OAI and SRS-RAN. And those software actually makes 5G actually accessible to security researchers. You can just download and git pull those repositories and deploy it in your like a standard Linux machine, and then voila, you have a 5G network to use. So more importantly, this software also provides virtualization capabilities, which means you don't need to buy any hardware equipment like a real base station, but rather you can use their IF simulation capabilities, install it in your standard Linux machine, and you can get a standard compliance 5G SA network and go. You can do your security research. But there's still many challenges on deploying those software, especially like they involve many complicated setups, like very complex command line interactions, many software dependencies. You need to go through the compilation process and properly configure the network to make them really connectable. So that becomes really a challenge for some beginners to use those software. And that's still there's a technical bar to use those open source software. And more importantly, in the community so far, there's no open source software that are really focused on security testing. like those open source software like OAI and SRSRAN, they do not provide security testing functions. So like if you want to reproduce some of the protocol level vulnerabilities, such as those I just now mentioned, it's really difficult. So based on those motivations, what we want to develop here is a platform called MobiDojo, facing the security researchers, and we open source it to the community so that they can, for beginners, they can easily use just one click to deploy a 5G SA network deployment in a fully virtualized environment using just Docker and the open source software like OAI. MobiDojo provides like a graphic user interface-based interfaces for you to monitor, control, and interact with the 5G SA network, and also involve doing reproduction of those existing attacks. And we also integrate MobiDojo with security testing plugins, like the security test suites we developed from our prior work 5G Spectre, and then integration with other existing tools like 5G Replay, so that you can replay those attacks with your testbed to test those security vulnerabilities. So this is a interface of MobiDojo. It's actually all open source, as I said, on GitHub right now. And it provides like a virtualization interface for 5G network topology, a control panel that allows you to control and interact, turn on the base stations, a log monitor to check those logs to see if there's any abnormal logs coming up from those network containers, as well as the security plugins for you to simulate and perform attacks. You can also use the PCAP modifier to create malicious like testing payload for you to reproduce attacks within this virtualized testbed. So as I said, feel free to check out the MobiDojo GitHub. We already open source it and provide some easy scripts and even like a video demo for you to guide you how to use MobiDojo and then what's the major function within the MobiDojo platform. So feel free to check it out. And then from a defense perspective, after we found those vulnerabilities and how we should defend against those attacks and vulnerabilities in the 5G space. So from a research perspective, how we should approach this problem. So in a traditional cellular space, like assuming you want to deploy some defense mechanism on the base station, but traditionally the base stations are just black box monolithic architecture. They do not have their source code open, and you don't have any authorized access to modify their source code to add some new security features. So what should we do? So we found that actually in 5G, there is some, 5G is actually moving towards a more open standard architecture that breaks the vendor login RAN implementation. So this is called the Open RAN or the ORAN. So ORAN actually breaks down the base station implementation into several logical units that are interconnected. So it basically breaks down disaggregate the traditional base station like the IF logic as the pure front end, and you have the backend logic like the control units, central units, and the data units that are interconnected through standardized interfaces. And the advantage of those standardized interfaces is that you can easily instrument those standard interfaces to get the data you want to implement many security features and functions on top of the black box base station implementations. And with that, the Open RAN also embraced the concept of software-defined networking that basically disaggregates the control logic with the data forwarding logic. So you can deploy applications called XApps on the control plane, like those lot of applications you can develop, including like traffic steering. You can develop AI. You can develop also security on top of the control plane to realize all different functions that are actually not available in the traditional 5G architecture. So that may seem a little bit complicated, but you can basically imagine the Open RAN is just like an operating system you can install on your base station. Just like on your smartphone, you can install apps from the Android App Store or the iOS App Stores. And all ORAN brings to the 5G base station is that you can install third-party applications, including security, including energy efficiency, including traffic steering, all those applications. And all that the Open RAN actually makes all this ecosystem more open and make this first-party installation possible. So we are actually the first group of people that are trying to following the ORAN standard to develop applications on security. We develop security XApps to help address those security vulnerabilities I just now mentioned. And one of the prior work, I also talked about this in the symposium last year, is 5G Spectre. where we developed the first ORAN compliance layer 3 cellular attack detection service to help mitigate the threats in layer 3. So I won't go into the details of this work, but basically what 5G Spectre does is that it can be programmed with any operator logic. Let's say we have a base station DDoS attack happening between the UE and the base station, that the UE tries to initiate like repeated patterns of RRC attacks to compromise the base station infrastructure. So by using the unique telemetry, we can program the corresponding rules, assuming the operator knows there could be a BTS DDoS attack, and that could be programmed within the PBS IDS signature within 5G Spectre that can be deployed into the Open RAN as a third-party XApp detection service, so that it can trigger some real-time attack alerts when the attack actually happens in practice. So 5G Spectre solved the problem of detecting some known attacks with known signatures. So what about unknown attacks? So we cannot assume we know every attack within the space. So how could we detect unknown and unseen threats that are growing in this community? And also another goal is how should we how can we classify and explain those attacks? So to answer this question, we recently developed another framework called 6G Exact that uses deep learning and recent large language model capabilities to detect and explain those attacks, which also deployed on the Open RAN architecture. So what 6G Exact, this framework does is that we use deep learning XApp to detect unseen anomalies and threats, as well as using large language models to explain those threats at the edge. So, I will just, due to limited time, I will just briefly talk about what this framework works. So MobiWatch XApps, we use like benign cellular traffic to train those XApp applications. And then we use like popular deep learning models exploring two different options, including autoencoders and LSTMs. And then the MobiWatch XApp is able to distinguish the runtime traffic, whether that runtime traffic is deviated from the normal traffic that it has been trained on, so that we can detect any abnormal traffic patterns that it may include some attacks and abnormal behavior within the network. And then we further use a large language model-based approach to explain those attacks. Like, because MobiWatch only tells you whether a given cellular sequence is abnormal or not. But we further go a little bit step further to further classify those attacks, explain why this attack happens under the 3GPP context, and how should we mitigate those attacks. And then we construct an LM-based XApp to detect those threats. And then we also develop a few more works to try to increase the reliability of the AI algorithms. We use like IG algorithms to fine tune or augment the LM's inputs and ensure the reliable performance. So to wrap up, we also have our own testbed at our 5G test lab at OSU. And then we also have our live demos we demonstrated on our websites. So all those demos and source codes are actually available on our website, 5gsec.com. We also open source many of the prototypes, and also the videos are available. And also I'm showing my contact here, so feel free to contact me, and I'm open to many collaboration from those both academia and the industry as well. So with that, I'm going to conclude my talk. Thanks for listening. I'm open myself to questions.